Hey, Nicholas. Okay, so I'm going to do these. I'm also going to leave them public in case somebody wants to see them. So this is question 3 from page, let's see, um, page 245. It's the one with the squirrel, and we got to use the double derivatives to find the inflection point. Now, first derivative is easy enough, but double derivatives are very good. But I want to point something out. Most of these double derivatives involve using the quotient rule. Okay, so the quotient rule is f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. But when we find either a point of inflection or a maximum point, we set this to equal to 0. We set this to equal to 0. And the quickest way to get rid of this denominator is to multiply both sides by this denominator. And you can see it disappears on both sides. In all these cases, the denominator will play no role. So do not spend time expanding your denominator and canceling out. You'll see that in some of the answers for sure. I actually find it's a waste of time. Just focus on your numerator. The second huge trick that I want to show you, which will make your life so much easier, is whenever you have a multiplier times an exponent, fine, just skip the multiplier. But you see this thing? When we write this thing over and over and over again and try to figure out when it's canceling and when it's not canceling and all sorts of things like that, it becomes a nightmare. It becomes a nightmare. And so what we're going to do is we're going to let the letter U, equal this thing for now. And then at the end of the puzzle, we're going to replace it. And you'll discover that if you do this, by the way, this replacement technique, very common in science and math, especially advanced math. It's the only way you can solve some problems. You might remember last year from the quadratic questions, but it's going to make things quite easy. And you know what? You can even do it right in the beginning. But I'm going to just leave it E in there till we go. So the first derivative is easy enough because there's only one. Whenever you take a derivative, you just find wherever x or t in this case is. That's the only thing that's going to be a derivative. So that's the same thing as this, which is 20 times all this thing in a bracket to the -1, which I've rewritten here. So I'll send you all these, so don't worry about it. Or you can take a screenshot. Which means, and the reason I do it like this is because I'd rather use the chain rule than the quotient rule. So that means, using the chain rule, I bring the -1 that's here in front. It's got to multiply the 20, becomes -20, becomes -2. And then I've got to take the derivative of what's inside. Well, that's an exponent, so the first thing is you just leave the exponent. And normally you take the ln of the base, but ln e is 1, so I didn't bother writing ln e over and over again. And then finally you have to take the derivative of the exponent, which is -0.02. So surprisingly, the derivative of this entire thing is right here. So it's not too bad. And of course, this part here just means it's on the denominator. That's what the -2 means. Now, I've left the -20 up here because it is not on the denominator. This -2 only belongs to this in the bracket. So it all goes down to the denominator. This will make it easier when I set it to equal to 0, because as I mentioned, we would multiply both sides by the denominator, and it won't play a role at all. It'll disappear. So that's why I'm going to do that. So I'm just going to put it down there. Now the -20 can multiply times -0.02 and it becomes positive 0.4. And I just leave this here like this. Now this is the first derivative. It's pretty easy. And there it is. And so I set that to equal to 0. We discover that this part disappears. And when we divide both sides by 1.2, we get this, and we discover, oh, this isn't possible, because when I ln both sides, or log both sides, ln or log of 0 is not possible. So that's why the first derivative doesn't have a 0, because there's no maximum min point. It doesn't have a maximum min point because it's essentially going to be an exponential curve, and it doesn't have, exponential curves don't have maximums. But I'll need this first derivative for the second derivative. So let's go. The second derivative, I'm going to use the quotient rule. I'm going to assign my f of x is equal to this. And therefore, my f of prime x is just going to be this. Yes, ln e is part of it, but ln e is 1. So it's minus 0.02 times ln e, but ln e is 1. So it's just the negative 0.02 that multiplies the 1.2 in front. So that just becomes negative 0.024. The reason I just make u equal to this part is because I want to get rid of all these numbers in front. They play a role. So I have this. Notice all this. I have this times that. That's f prime of x. G prime of x is this. I got to use the chain rule. I got to bring the 2 down in front. It becomes a 1. Then I got to take the derivative of everything in this bracket. Well, the 1 is 0, so it doesn't play a role. The derivative of an exponent is going to be the entire exponent times the derivative of the base, which is, or sorry, the ln of the base, which is 1, times the derivative of this part, which is minus 0.02. So I get the minus 0.02 times ln of e, which I never write, times the entire exponent. The 1 plays no role here. The 1 plays no role here. And if I look very carefully, I can say, okay, well, you know what? I'm going to expand, and this is just badly written here. I'm going to leave this entire thing in the bracket, this 1 plus 3 to the power of negative e2. And I'm just going to put it there. And I'm just going to put this 2, and I'm going to multiply the number, because all numbers in front can be multiplied and put in front. So 2 times the negative 0.2 times the 3, and I get negative 0.12 times this times 1 plus this. And I just for sakes, I've written down what gx squared is, which would go in the denominator. Now, it's at this point I'm going to let u equal this. So everywhere we see this, everywhere in all these things, just the e part, I'm going to replace it with u. So if we look very carefully, and I didn't bother writing it, but if we look very carefully, f of x just becomes this, 1.2 times u. That's a lot easier. F prime of x just becomes this, negative 0.024 times u. A lot easier. G of x just becomes 1 plus u squared. That's a lot easier. And why? Because often the u will factor out. You'll see it in most of these. And then, of course, g prime x, when I look here, oh, here's g prime right here, it is actually equal to negative 0.12 times u times 1 plus u. Not too bad. Now, you don't want to do any expansion at this point. Just leave it like that. So then I use the quotient rule, and I write the quotient rule. There's g of x times f prime of x. I've taken all these red values, and minus, it's always minus, and then it's going to be f of x, which is this lovely 1.2u, times my g prime of x, which is right there. Now, you don't have to expand it yet, and actually, I probably made a mistake expanding all this stuff, because if you look carefully, wherever you see a u, so I can see there's a u multiplying, I could have factored it out right away. Then when you divide it on both sides, it disappears. So I could have gotten rid of this u and this u. I can't get rid of this u because it's in a bracket being squared. And technically later on I can get rid of this u. But I don't do that. I just stick with long form expansion. So what do I do? Hang on. As soon as I do that, hang on. I got all this stuff going on here. It's not disappearing. Doesn't matter. I'll just get rid of it. All right. So what do? I expand this. That's a simple a plus 2ab plus b squared. So 1 plus 6u plus 9u squared. And it's going to be multiplied by this and u. And again, I should have just factored the u in front and not expanded it. But I do. And so that it means everything in here gets a u higher up. So this is what this bracket expands to. And then when I multiply it by this, that's what you get. On the left side, I did the same thing. I multiplied this times that, that's that, and this times that, times that. And then, oh yeah, oh sorry, I just multiplied these two. I left this all alone. And then on the next stage, I expanded it. Again, I think it's a colossal waste of time. I didn't have to expand it like that. But right away, I can see this negative makes everything in this bracket positive. And so then I get a minus 1.44u squared plus 1.4 squared. So those canceled out. And again, I have too many u's. I could have just factored out a u very early. But I get up with this. So because the 0.432 plus 0.216 u cubed is here. Okay, minus the only u. That becomes 0.216 u cubed minus this. Then I factor out a u out. Should have done it much easier. As a matter of fact, you can probably factor out a lot of these numbers earlier. And then once I factor a u out here, I can divide both sides by u, right? Because u is going to be equal to 0, or anything in the bracket's going to be equal to 0, just like normal factoring. Which means only the brackets of my concern. So I make it equal to 0.24. I divide both sides by 0.216. I get u to the square is equal to 0.024 divided by 0.216, which is 0.333, but more accurately, it's 1/3. Oh, sorry. It's that, and then the square root of it is 0.33. And when you take a square root, you got to do a plus and a minus. Now, more accurately, that's 1/3. So now I bring back what u was all along. U was this. And I only make it equal to the positive, because if it was equal to the negative one over here, and I take a ln of both sides, there's no such thing as a ln negative. So that one's ruled out. So I go to here, I bring back my e, and I make it equal to my positive 0.33. I take a ln of both sides, and so this is I kind of skipped that. I should do it more clearly. The only way you can solve exponents with your new knowledge is you take a ln of both sides. So it becomes ln of e to the power of negative 0.02t is equal to ln, open brackets, and here I'm going to use a third, because a third's more accurate and easier to type. Now the rule of exponents for ln is I can take this exponent and put it in front. And so it's times ln of e is equal to ln of third. Well, a ln of e is 1. So that's why it jumps down to this line. So I get negative 0.02 is equal to ln of a third. I divide both sides by negative 0.2. Any ln of a fraction is going to be negative, by the way. So ln of a third divided by negative 0.2 becomes t is equal to 54.9. Now I encourage you always, always, always. So 20 over 1 plus, I'm just going to move this so I can type it in. And I'm going to do that. An expression. I'm going to bring it up top. And I'm just going to put an x to make it easier for Desmos to do it. So this is the thing we're working with, 3e to the power of negative 0.000, or yeah, there's just 10 x. I'm going to use x. Now I'm going to turn off my other stuff because that's the future graphs coming on. But I'm going to put in a couple of points that we just discovered. We just discovered the inflection point, or the second inflection point, or the inflection point rather. We've discovered that it's at 1 over, sorry, what did we discover? Let's bring it back. Yeah, we took the second derivative and we set it to 0, and we discovered it's ln a third divided by negative 0.02. Okay? So that means that p, or sorry, bracket, ln of a third divided by negative 0.02, comma, p of that. And I'm going to change the p. I'm going to change it to q of that. No, t of that, because, yeah, because we have it later on. And I'm just going to put all of this into there, and it's going to plot the point for me. I'm going to label it. I'm going to turn off all my other graphs. There we go. Oh, wait, that's not the point I'm looking for. I'm going to get rid of that. There we go. I'm going to hit home, and hopefully it comes up. There it is. Now notice that it's stretched too much. I'm going to just shorten my x-axis to maybe 5. And I'm going to shorten my y-axis to 0 to 20. Oh no, 100? No, 20. And then I'm going to make this really long. There we go. That's a bit better. How about 500? There we go. And sure enough, notice that this is just the point 10. And this I could just put in as the original thing, but 2 divided by ln 2 is more accurate than this number here. And that is the point of inflection. It's pretty clear it's the point of inflection. You might say, what's the definition of point of inflection? It is the point when the graph was going up, right? And then starts going down. Points of inflection are the fastest point or the highest slope of any graph. And they answer a lot of questions in certain scenarios. And in this case, it tells us when what was the original question about? It tells us when the squirrel population was growing exceedingly fast and then started to slow down. So that was when the squirrels were having the most babies, essentially. And population growth is very huge in science, and they don't have a really good way of studying the environment other than measuring the population, because the environment has so many influences. It's hard to contain it. When we do chemistry, we contain it in a sphere so that we can keep all the conditions stable. Anyway, so we've determined the point of inflection, and if we were to explain the point of inflection, it means that that's the fastest period of squirrel growth, and it's going to slow down after that. So you can even see it from the graph. Squirrel growth growing up, faster, 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 slowing down, slowing down, slowing down. So that's always point of inflections. When does the graph start to curve the other way? You'll see point of inflections in cubics, quartics. You'll see 3 points of inflections in quartics, 2 points of inflections in cubics, 1 point of inflection in, oh, actually, I don't think you'll see any point of inflection. I think it's 2 off the degrees. You'll see 1 point of inflection for cubics. Now, I want to introduce something useful for you. And speed up here and there, but don't ever skip. I can also tell Desmos to find my first prime and set it to 0. And Desmos won't draw it because there was no first prime in this case. There's no maximum to that curve. But I can tell it to set my second prime, which is the second derivative, to 0. And be sure to name the proper, so this one was t. And Desmos will draw a straight line up and down through that point. It's very annoying in that it won't identify it for you. You have to draw a horizontal line through it and measure. But if you've gotten the point correctly, it will confirm it for you. So you can see that the point of inflection goes through our dot. You might say, why is our dot slightly off as I zoom up? And that's because instead of using this, I used numbers. So I should actually use the very specific of this to get right on the point of inflection. Because as soon as you do decimals, you're no longer accurate. Okay, so that's the first one. Always use your Desmos to confirm your answers and even understand the curves we're talking about. On to the next one. So the next one is all about so there's the squirrel population for those of you who weren't sure which one I was doing. Next one's about net monthly profit, which we did the first and second derivative together, but I'm going to do with you to show you how much easier it is with you. Obviously, the annoying thing in here is that. If we just make that the letter U, might make our lives a little easier. Be careful. You could also expand this fully and get rid of a lot of 10s to the 6s, but it actually affects the answer. And that's because this -1 becomes important later on in solving it. So you have to include that as f of x, this x minus 1. So I will instead expand it and then take derivatives. So determine the item's yield at maximum profit. That's when the first derivative is equal to 0. And they tell us our domain goes from 0 to 2,000 items maximum. That's what it means. They don't ask for a second derivative, but I will do a second derivative. And they tell us it's 500 items. What happens is 500 items. As we already explained, as we will see from the curve, 500 items is the max point because it's on the way up to the max point. Anything to the left of a max point is a positive slope. Anything to the right of a max point is a negative slope. Therefore, if that's the maximum items we can build, that is also the max point on the graph. We will look at our steps here, though. Let's see which one it is. Ooh, that's the complicated one, I think. Yeah, here we go. So in this one, if I take, I expand this 10 to the 6, I get 10 to the 6 plus 10 to the 6 times this. This is the one I'm going to leave alone right there. And so I'm going to treat it like this. 0, and this is, I got to take the derivative of this, because the derivative of that is just 0. And that's the product rule. I make my f of x 10 to the 6 times x minus 1, and the f prime is 10 to the 6, because if I were to expand that and take the derivative, it's just 10 to the 6. My gx I'm going to make, so that means I'm going to make u equal to this. Just going to make my life easier. And I'm going to just call it u. But for me to get the proper derivative of g of x, if I take the derivative of that, it's the derivative of the base, ln e, which is 1. So it's 1 times the derivative of the exponent, negative 0.001, like that, times the derivative, or times the exponent itself, So as you can see, the only thing that got in front is the negative 0.01 times the original exponent, right? Times the original exponent, which we're calling u. So I'm going to just call it negative, the derivative, negative 0.1 times u, and make my life easier, like that. So that means g of x is equal to u, and g prime of x is equal to negative 0.1001 times u. Then I just go through the whole thing. Now, word of advice, right here, I can see that I have a u timesing this bracket, so I can just treat that bracket like its own unit, timesing 10 to the 6, and over here I have 10 to the 6 times u. Technically, I should factor out 10 to the 6 and u, but I wanted to show the steps. First, I factor out a u, which means I take this entire thing and anything in between pluses is what I'm factoring out. So I divide u, and the u's cancel, and that goes in front as a u. If I were to divide this whole thing by u, the u's cancel, and that would go in front. Just to make sure, you can always expand it. So u times 10 to the 6 times minus 1 times minus 1 becomes this. And u times this second thing becomes that. So it's factoring. When I divide u on both sides, it disappears. That's why we make it u. Now you can see I don't have an exponent in there at all. It's just x, going to make my life a lot easier. Now I've left the 10 to the 6 in at this stage, but now I'm going to factor it out. I'm going to bring 10 to the 6 in front. So whatever's left here, I've divided by 10 to the 6, and over here I've divided by 10 to the 6. When I divide this right by 10 to the 6, it becomes 1. And when I divide this left by 10 to the 6, it becomes open brackets, close brackets, x minus 1 times this. And 10 to the 6 is in front. If you want to make sure, you can expand it and make sure. And I divide both sides by 10 to the 6, and it disappears. Now I'm left with this. I add 1 plus that. I get 1.001. I bring it to the other side. It becomes negative 1.001. I divide both sides by negative 0.1, which is, oh yeah, I expanded that. That's what I've done here to get to there. Then I've added the 1 to the 1.01. Then I subtracted it to that side. So I get this is equal to negative that. Divide both sides by negative 0.1. I discover that x is equal to this. And since it's a first derivative, that's going to be a max point. Now the best thing to do for a max point is take the derivative just to the left. So a good number just to the left is 0. So we would put 0 in anywhere here. Back before I started factoring out zeros, we would take the derivative, we put in 0, and we discover the slope is positive. Now I didn't take the second derivative of this because this one didn't ask it, but I did take the graph. So we're going to look at the graph. I'm going to get rid of that first graph. We don't need it anymore, right? And here's the second graph. Now to see it, because the things go way up high, I have to go to about that, and I have to make my x like 10 to the power of 8 in order to see the graph. Even worse, 9, I think. There we go. In order to see the max of the graph. And now according to me, and this is, according to me, I'm going to get rid of this graph. Oh, no, I'm just going to turn it off for now. And I'm going to go up to this graph. I'm going to add 1. And according to me, 1001, comma, p of 1001 is the max point. And sometimes the question will ask you, what is the max profit? And you should put 1001 into the original equation. And we discover the max profit is 3.6 times 10 to the 8. 10 to the 6 is a million, so this is $368.5 million when you sell 1001 units. Now there is no inflection point. Actually, there would be an inflection point right over here because it's coming down and then it flattens. So, but because they put a domain restriction, they said the most number of items we would manufacture is 2,000 items. This is actually the graph you should be using. And that's because anything to the left is negative items, which we don't have, and anything below the x-axis is negative profit, which doesn't concern us. You'll notice that their profit goes up, and then at 1,001 units, it starts going down. That is not a point of inflection. The curve is going down, 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 down to there. The point of inflection actually equals later. And I probably should have taken second derivative just to show you how to find the point of inflection. But we will take P double prime of x and make it equal to 0. And I think I have to make capital P because I made it the function capital P. And we discover that this is the point of inflection. Notice it doesn't quite tell us. Now, I should have taken the second derivative and solved that just for doing it, but I didn't because it didn't ask. On to the next one. The next one is long. So the next one is all about, oh no, that's the first one. So I'm going to go over here. The next one is question 14 in the textbook. And it's right here. You have just walked out the front door. So this is a door swinging open that's measured. You notice that it closes quickly at first, then closes more slowly. In fact, a model of the movement is given by D based on time is equal to this, where D is the number of degrees between the door frame and the door. Okay, so let's look at a visual of that. I'm going to go over here. I don't want to delete it because I'm going to be sending this to you. So if I open a door like that, and then I open it, right? Let's look at the door frame. I'm going to put a door frame down. That's my open door frame. And I'm going to put a gap in it. And I'm going to call that gap the door in red. I'm going to make it red so we can see it. When it's closed, it's 0 degrees. That's about 10 degrees. That's about 45 degrees. When it's straight up, it's 90 degrees. You can even open doors wider, as you know. And the most I can open this door is 180, technically. I mean, most of the hinges would break. But this door is opening like this, and that's the degrees. The D of t is this here, the angle. It's not the distance. It's not the distance. It's the angle. So it's based on time and seconds. So my guess is the door will, if you imagine a spring-loaded door, you'll open it fast, then it'll close, and then the spring will hit, and it'll start closing slowly. And those last little bits are really slow. Okay, so visualization always helps. Well, here's our model. Oh, that's the wrong one again. Here's our model, and as you can guess, I'm going to replace this part, the exponent, with the power for u. And this is actually a very easy derivative. It's just the product rule of these two things. The product rule states this. F of x is 200t, f prime of x is 200. G of x is to the power of negative t, but we're going to make it u. And g of prime is just the negative 1. It's going to be the ln of 2, right, the ln of the base, times the derivative of this exponent, which is negative 1. So it's negative ln 2 times this exponent. So we discover it's negative 1 times ln of 2 times the exponent. But we're going to call that exponent u. So we're going to rewrite it as negative 1 times ln 2 times u. It's going to make our derivative life a lot easier because u often factors out. That means if I put it into here, f of x is 200t times g of x, or g prime of x, which we've determined is this, plus g of x, which we've determined is u, times f prime, which we've determined is 200. As you can see, there's going to be a u on this side, on the right and the left, and there's a 200 on both sides. And there's almost a ln 2, but there's not. Well, just to make things easier, the first thing I'm going to do is factor out a u. When I factor out a u from this left side, I get minus 200 times ln 2. And by the way, I missed the t. I forgot to write the t here. There's a t. And actually, I'm going to write it a little bit. I think I meant to include it later. So I'm just going to put this here. Maybe I can do it like this. Down below, and I got to remember to put a minus in front. There we go. Because it's minusing the minus 1. There. Now, I factor out a u. So this is what's left in here is minus 200 times ln 2 times t. I've just moved the t over here to the right and put all the numbers in front. And on the right side, when I divide out a u here, I'm left with 200. Now I've just left the 200 in there. I didn't really need it. I could have factored out the 200 as well. So then I'm left with this, because I divide both sides by u and it disappears. That's why we make it u. It makes it a lot easier. I'm left with minus 200 times ln 2 times t. And when I bring this 200 to this side, I get equals minus 200. Then I divide both sides by minus 200, which is why I could have just factored out the 200, because it becomes ln 2 times t is equal to 1. Then I divide both sides by ln 2, and I discover ln t, when we make the first derivative equal to 0, it's going to be a max point, or a min point. We'd have to prove it's a max point, but I'm not going to. That's up to you. And we discover that this is the time that the maximum point of the door swings the widest. And if I put this into the original formula up here, if I put that time wherever I see t, I get it's 106.15 degrees, because the measurement is in degrees. So it's past 90 degrees. It's actually like that. There's the door, and it's going to swing shut. Well, to find the next question in this question, so they ask us several things. Graph this relationship. As I said, you should just plug in time is 0, time is 1, time is 2, time is 3, and you'll get a good idea of the graph. And you and I discovered between 1 and 2 it hit the max point, went up and came down. Determine when the speed of the moving door is increasing and decreasing. So that's to the left of the max point, it'll be increasing, and to the right, it's a max point. So to answer that question, it's all the way from 0. It's all the way from 0. So in notation, it would be 0, including 0, comma, 1 over ln 2. Close notation is when it's increasing. And then close bracket. Oh, actually, it's a round bracket here because that's the max point. It's neither increasing nor decreasing. Then round bracket 1 over ln 2, all the way to comma positive infinity, because we discover on the graph, if I put 1,000 up here and 1,000 here, let's try it. 200 times 1,000. 200 times, well, let's take 1,000,000. 200 times 1,000,000 times 2 to the power of 1,000,000 negative equals. Oh, so let's do the 2 to the negative million first. 2 to the power of 1,000,000 negative equals. No, it's not invalid. 2 to the power of 1,000,000 is just 1 over 2 to 1,000,000. 1 divided by 2 to the power of 1,000,000. I don't know why it's doing that to me. And that is not true at all. Is it just not? Okay, let's try 1,000. I don't think it can handle a 1,000,000 maybe. 2 to the power of 1,000 negative equals. There you go. It just didn't want to see. It's a really tiny number. It just didn't want to do it. Then we're going to multiply it by 200, which is multiplying 1,000, because the time I'm taking here is 1,000. We discovered an impossibly small number, but guess what? It's not 0, which means this door never closes. It's never going to close because this can never result in a 0. There's no amount of t I can put in here, because 2 to the negative t is just 1 to the 2 to t. And if I put 1,000,000 in here, this is just a really tiny number multiplying a fairly large number, but this is way tinier because exponentials get bigger faster. But it never closes. This never becomes a 0. So we discover it's never going to close, so it's always going to infinity. Now, the second derivative, okay, so now here's the beauty. You see right here, that was my first derivative before I started factoring out u's and whatnot. And even, yeah, even there. I'm going to keep this one as my first derivative because they're being added. So I can just use the product rule on this side of it, where t appears in u and t, and that's just a normal derivative there. I've rewritten it out without the u, just to show that this side is just a normal derivative. normal exponential derivative, and this side's the product derivative. But see, if I'd expanded all this into one sort of thing, I'd have to use the quotient rule again. Much easier if I keep it in this format, unexpanded. That way I can do the product rule on this side and just normal derivative here. Well, first I do the product rule. Keeping it in factored form makes the second derivative easier. Product of this derivative, I've defined this as f of x. So 200t. The derivative of that is 200. Then, again, I'm going to replace this as u, but I'm going to take the derivative of this first to show you. Well, g of x is equal to this, right? Right there. But I'm going to replace that part with u. It's going to make my life a lot easier. Then I'm going to take the derivative of this. Well, the derivative of this part of it is ln 2 times negative 1. So that means I'm going to take 1 times ln 2 times ln 2. Oh yeah, because it's always minus 1 times ln 2 times minus 1 times ln 2 becomes positive 1 times ln 2 times ln 2 times 2 to the negative t, and I've replaced 2 to the negative t with u. I've kept this here because I know I'm probably going to factor out a ln. So I've just kept it ln. Now I've got my f of x. Now I want to point out again, when we set the second derivative and we get g of x squared equals to 0, I multiply both sides by g of x squared and it disappears, which is why I haven't bothered with g of x squared. Oh, actually this is a product rule, so I don't need to do g of x squared at all. Another benefit of doing the product rule. So I follow the product rule, I fill in the stuff. Notice I'm not expanding it. That's because I got a 200 here, a 200 here. I got a ln 2 here, a ln 2 here. I got a u here and a u here, plus in between. So I factored out a 200, a u, and a ln 2. When I factor that out from here, I'm left with ln 2 times t. When I factor all that out from here, I'm left with minus 1. That's the only thing that's left because that's gone, and that's gone, and that's gone. So I get ln 2. Now, it's going to eventually be, I can't set this to equal 0 because I'm adding it to this. So we'll just leave it like that. We just left it as a factored form, okay? Now I'm going to do this right side. That's an easy exponential derivative. I take the exponent itself, I multiply it by the ln 2, the base, and the derivative of this, negative 1. So I get negative 1 times ln 2 times the exponent itself. Now, this part of the exponent I'm going to replace with u. So I get 200 times ln 2, negative 200 times ln 2 times u. The negatives can really mess up, so don't miss them. Now I combine them the way I've combined them here because it's a plus here. So I get the product rule plus my normal derivative, but because my normal derivative is a negative, I've replaced the positive with a negative. And I get notice I got a 200 times u times ln 2 times ln 2, and this is its own bracket, so I'm just going to leave it as its own bracket. But this bracket is being multiplied by this stuff here. Well, notice I've got a 200 and a u and a ln 2, a 200, a u, and a ln 2 here. I'm going to factor that out. I'm left with this bracket right there, which is ln 2 times t minus 1. And when I factor all that out of this, it's minus 1. Because I divided everything on both sides. If you want to prove it to yourself, just expand this again, and you'll get back to that. Okay, now this is all set to 0, because this is the full second derivative, equals the inflection point, equals to 0. I can divide, because this is multiplying this entire square bracket. I can divide this on both sides and it disappears. And I'm left with what's in this square bracket. Well, what's in this square bracket is ln 2 times t minus 2, because it's minus 1 is equal to 0. I bring the 2 to this side. I get ln 2 times t is equal to 2. I divide 2 ln b2 on both sides. I get t is equal to 2 over ln 2 will be the inflection point. Let's go to the graph. I'm going to turn off all my other graphs. Here's the graph. I claim that the point of inflection, oh yeah, so I'm going to turn that graph on. I'm going to hit home and maybe see it. There we go. Notice it's going to go way up again. So I got to do from 0 to 10 or so. And from the y-axis is going to go from 0 to 180, let's say, like that. So we already figured out the max point should have been, we're going to get rid of that, and we're going to get rid of that. We figured out the max point should have been at 1 over, what was it? Let's go back to the max point. We figured out over here. Yeah, 1 over ln 2. Oh no, that's just the, yeah, 1 over ln 2. We figured out was the max point. Now if I put in d of 1 over ln 2, that's what I get, 106 degrees. I can do that, or I can just put in as my x values 1 over ln 2, comma, d of 1 over ln 2. And then Desmos will draw it for me. There's my max point. Or I can just figure out what 1 over ln 2 is. It's about 1.44. Notice that the decimals will never be as accurate. Comma, 1 over 6.147. You can do it either way. I like having Desmos draw it for me, but you're often going to have to figure out what they often ask, what is the max the door opens. Then you can take the first derivative to the left, set it to 0, or not set it to 0, put 0 in for x to see if the positive slope is on the left, negative slope is on the right, and then you'll know it's a max point. Now, according to me, our second derivative, which will be the inflection point when the door is swinging fastest, is 2 over ln 2. So we're going to let Desmos draw it for us. 2 over ln 2, comma, d of 2 over ln 2. And we're going to have it drawn. Now, it doesn't quite look like that's an inflection point, does it? I'm going to get rid of my max point for now. And that should be the point when it's moving the fastest. Now, if I'm not sure, I can say, okay, d double derivative of x, set it to equal to 0, and it'll draw a line straight through the inflection point. Didn't look like it, but it is. That's because the door is swinging the faster and faster and faster closed, and then it starts swinging slower and slower and slower. And that's what an inflection point. The ski hill is, it's most exciting at that point. That's the steepest part of the ski hill. And so you go down the ski hill, down really fast, and then the ski hill's got to flatten out sometime. So this door is closing. Now notice, as I mentioned, no matter how far to the right I go, it's never hitting the x-axis. It's always got a space there. But if we look visually at it, we could sort of say, okay, well, technically, I will say that this door looks like it's closing or closed from about 10 seconds onwards. But if I was going to get the official answer is this door never closes. It's not a good model. It's only a good model for this part of it. So I discovered, yep, when I set my double derivative equals 0, it's indeed that. And guess what? You can set your single derivative to equal to 0, and it will confirm the max point for you as well. Like that. There we go. So when I set my single derivative equals 0, it'll draw a line through my max point. When I set a double derivative equal to 0, it'll draw a vertical line through my inflection point, and I can prove to myself that I got the right calculus. Very difficult, but when you know these tricks of replacing it with u, factoring things out, not expanding, it makes it a lot easier. I find when you expand the first derivative into its simplest form, it just makes the second derivative that much harder. Sometimes it's good just to keep it in an expanded form and use that, because the derivative of that's still going to be the derivative. And when it's in its fx times g prime of x plus g of x times f prime of x, it's now just the addition of two product rules. Makes a second derivative a lot easier. Hope that helps.